excited to introduce our speaker. And as usual, I will tell you what's going to happen a week from now. And then actually, today is our last seminar this semester. So if you are celebrating your Thanksgiving, you don't need to come back, okay? And so this is the last one. Okay, so Shelby is actually she's local. She's from UMD, from right here. And in fact, one or some of you here actually is taking her class. So very, very local. So Shelby is from civil engineering, and then she did her PhD at UC Berkeley. And after that, so in her PhD was also in civil engineering, but it was more about like construction and seismic risk. But after that, she took the career path to work for nuclear, what is that called?
Nuclear Regulatory Commission.
Yeah, very, very local. For some years. And then I asked her why she moved back to UMD. She said, I got bored. I like teaching, actually. I like interacting with students and research. So now she's back in a civil engineering department. And also because of her past experience, now she does a lot of risk analysis specifically for nuclear power plants. So for construction modeling, she can analyze and understand what's a risk and then probability. So that's sort of related to her talk today, because those kind of risk analysis, it can be applied not only to nuclear risk or seismic. It can be landslide, it could be climate change, it could be flooding, it could be a lot of different things, as long as you know what's the mechanism in the physics or interaction. So today her talk is resilience and risk-informed decision-making for natural hazard events. Let's welcome her.
Do I have to do anything to turn this on? You good? Okay. Yeah, so I'm over in the Department of Civil and Environmental Engineering. So I'm kind of an engineer by training. My PhD and master's degree in engineering, but actually my bachelor's degree is in economics, so, risk. All right, so I'm also affiliated with the Center for Disaster Resilience. So I'll talk a little bit about what disaster resilience means. And I'm also affiliated with the Center for Risk and Reliability. So the common thing behind all that is probability. So I do a lot of work in probabilistic stuff. So I'll be sharing. So I'm going to talk a bit about what is resilience, what is risk-informed decision-making, how we approach this in the field of resilience engineering. And then I thought at the end I would just share just a little bit of snippets of some of the research that I'm involved in, so you could get a feel for the type of work that somebody like me might be doing in the area of resilience engineering. So without any further ado, I guess I'll get rolling. So natural hazard events. So I have to write proposals, right, and papers, and the news gives me lots of things to say why natural hazards resilience is really important. So this map here shows the number of billion-dollar-plus events that have happened this year up through September 2018, September of this year. So this does not include Hurricane Michael that came through and did a number on Florida. It doesn't include the Camp Fire that's going on right now in Southern California. So this is just going to get worse as things go on. So when we think about even just these big disaster events, we often think about the things like Hurricane Florence that came through and created a lot of flooding in North Carolina, and wildfires in California. These things make the news. We know about them. But there's also a lot of other natural hazard events that actually have costs that exceed $1 billion. So one of the examples being we had some drought events going on in various parts of the country this year. This map here is just showing locations that have been below average or significantly below average in terms of their annual precipitation. So while we've been having a really, really, really wet year, there are places in this country that have had really, really dry years, and these actually do lead to losses in excesses of $1 billion. Hail events. Actually, there are a number of hail events that have happened this year that have exceeded $1 billion. When I first started looking at this, I was like, how many broken windshields do you need to exceed $1 billion? Well, it's actually not the broken windshields and the damage to the houses. agriculture gets hit really hard. So we think about agriculture and drought, but hail events are actually pretty significant for agriculture, and agricultural losses in natural hazards events are pretty significant. Even hurricane events, when they go through Florida, have a huge agricultural impact. So that actually does pump these losses up above what I think a lot of us think of when we think of natural disasters, which is how these disasters hurt our houses and our roads and our infrastructure. But a lot of these events have a lot of impacts outside of that. That was 2018. 2017 was a pretty bad year for natural hazards events. We had a large number of events, not just hurricanes, but tornado events, and there's actually a freeze event that happened in the southeast that once again had a huge agricultural impact. But fires, droughts. 2017, yeah, I was just noting some of the pictures here. Hurricane Harvey came through. That's been a pretty substantial event in my world in terms of the fact that a lot of flooding happened where people didn't expect it to happen. Although, as a person who works in this area, I would say that this was not in any way unexpected. You pave over everything without zoning codes, and you put people inside flood pools with things where water is supposed to go in a large rain event, and you're going to have those types of events. So this is up here as a weather or climate disaster. I argue maybe it's not a weather climate disaster. This is in many ways a man-made disaster. So we had a couple of the hurricanes and some tornadoes come through. 2016 wasn't that much better. So if we look at some of the how in the left-hand figure there, we're looking at the number of billion-dollar plus in adjusted terms, so this is all CPI adjusted terms, how the number of billion-dollar plus events we've had dating back since 1980, and then on the right-hand side, you're just seeing the annual cost. So you can see there's definitely a trend here. We're having more and more of these, and once again, these are adjusted. So this is not that damage just costs more. This is actually that we're having more of these events. This is not entirely due to the fact that we are having more severe weather and climate events, for example. This is also due to the fact that we continue to build closer and closer to the coast. We continue to build at the urban forest interface, so that when we have these wildfire events that previously would have just burned, now they're having significant destructive impacts on communities because we keep building and building closer to those areas. So the fact that we're having these disaster events is not just about the hazard. It's about what we are doing in terms of our built infrastructure and what we're doing to our natural infrastructure that is making these events that, in some ways are just natural events become natural disasters and having these huge economic and other types of impacts. And I do want to note that here I'm focusing on these big ticket events that have huge dollar totals, but we also are seeing an uptick in the number of smaller scale events. So if you've been watching the news locally, where we had Ellicott City has experienced some pretty large floods in 2016 and 2018, and we think that they're new, but it also happened in 2011 and back because you put your city in a river, and that's going to happen. But you have these events happening locally too, or you have the increase in nuisance flooding. That's flooding that just happens, several times or more throughout the year, where you're having communities cut off because roads are being flooded due to tidal effects, for example. So we have this issue where we're having both an increase in these big honking disasters as well as these more nuisance level or local level events that don't make the national news, but are really, really important for the local communities that are affected by them. So this is not like engineers have not been trying to solve this problem for years and years and years. But the thing is that conventional engineering approaches, the approaches that we used up until the last couple decades, they've really relied on what we refer to as resistance as the means of overcoming or minimizing the damage to natural hazards. But when we talk about resistance as engineers, we're talking about trying to make our structures bigger, stronger, beefier, trying to resist the loads that the natural hazards can place on them. Now this is a problem because you have to choose how strong to make your structure, and at some point it's going to fail. And there's only so much you can do to resist loads. So despite the fact that we've been trying to use these approaches where we try and make things bigger and stronger, we still continue to have this escalation of losses. So really what we need to do is we need to, in engineering in particular, we're starting to say we need to rethink the approach that we're using when we think about engineering. And so that's where we've come up with this notion of resilience engineering. It's actually a different engineering paradigm. We're trying to look at disaster loss and avoidance differently. We're still going to have to build structures to be strong and resist the loads that can be placed upon them, but we're looking at this in a little bit more multidisciplinary way. So we're looking at policy decisions that can impact our losses. So let's stop putting structures in the floodplain, right? Let's incentivize people to not put their structures in the floodplain, incentivizing people to buy insurance. Having building codes. You think the building codes sound like a no-brainer, but there's a lot of communities in this country where there are no building codes that have been adopted and required at the local level, requiring certain types of structural robustness. So that's part of the sort of community planning. Education and preparedness. What does it mean to be prepared for these hazard events? And then thinking about working things like environmental protection. For many years, we focused on things like hardening our shorelines with revetments and bulkheads, so piles of rocks and vertical walls. But now there's a big emphasis looking at more living shorelines. This, looking at how mangroves, we just saw a presentation earlier today about how effective mangroves are at protecting shores during hurricane events. That's the folks at the Naval Academy are looking at that particular issue. Or wetlands, and restoring wetlands as a strategy for increasing our coastal resilience. So let me define resilience. Can't see at the definition at the bottom. This is not my definition. I've adapted it from the national academies. So when we think about resilience, it's the ability of not just individuals, but communities, private organizations, government, to plan and prepare for natural hazard events, respond to them, recover from, and adapt to them. So we're not just saying we want to build things bigger and stronger, we want to plan for these things, and then what we want to be able to do is we know that these events are going to happen, so we want to design for our ability to rebound from them effectively. So we know we're going to get hit with these natural hazards events, there's nothing we can do about it, there's going to be some damage, but do we have the capacity to recover quickly without resulting in adverse impacts or disproportionate impacts on certain populations that we have in our communities? So that's resilience. So disaster resilience is really a complicated problem. And I only work in one small piece of this, so it involves a number of things, and I've got engineering at the bottom because I think that's probably, in the great scheme of resilience, probably where it goes. Even as an engineer. So it's involving a lot of factors such as social behavior and cultural considerations. So the cultural composition of a community can affect their willingness to listen to local officials and their trust of local officials. It can affect preparedness. Where do community members go in an event? What are their community leaders when we're trying to get folks to change the drainage of their yard? Who do they trust in terms of telling them that's a good idea? Of course, this is all economics and finance. If you want to take measures to make your community more resilient, how do you pay for that? There's an entire research discipline on bonds and funding and resilience. Of course, public policy and the regulations that we put in place. Public health is a really complicated part of resilience in terms of how do we ensure access to health care during disaster events. I learned recently that the average American, on average, our prescription use is 3 prescriptions per person. So on average, so some people have none, but some people have significantly more than that. So when you're talking about post-disaster environments, and the ability to get the prescriptions you need is to sustain your health. We're not just talking about acute issues, we're talking about chronic issues that can become acute in the aftermath of a disaster. And of course, those of us here in the physical sciences and engineering, we matter too, but we're only a piece of the resilience puzzle. All right, so I work in the area of risk assessment and risk-informed decision making. So this is just one piece of the overall resilience, the overall issue of disaster resilience. So if I ask what is risk, what do you think? What is risk? When I ask you what is risk, what do you think of? A gamble? Risk, you think of it as a gamble? Any other thoughts on what risk is? What does it mean something to be, what is a risk?
Something wrong to happen.
Something wrong to happen? Something bad things happening? Oh, good things. That is a very deep philosophical question I'm going to skip. So there are things, there is actually a fundamental question is when we're doing risk assessment, should we be thinking about the good things too? Maybe, but we don't. So that's a deep question. I'm gonna pass over that. Yeah, so in essence, risk, a lot of people do talk about risk and they think of gambling and chance. They think about the probability piece of risk, but risk actually involves three key components: what can go wrong, how likely it is, and what are the consequences of it. We call this the risk triplet. This goes back to an article in the 1980s, but it's become so ubiquitous now that we actually probably can throw this up without even citing it anymore. So what that means is we have to think about, what are the scenarios that can happen when we're talking about a natural hazard? What are the probabilities of those various scenarios? And then what do those scenarios, what are the consequences of those scenarios? Once again, usually we think about this from a pessimistic perspective, consequences, not what are the good things that can happen. So this is our risk triplet. In natural hazards assessment, we break it down. There are different ways that different people break this down. This is an adaptation I've done on a FEMA approach, where we break down the elements of disaster risk assessment into sort of 5 key blocks. The first is hazard analysis. So we have to understand what hazards we're talking about and what hazards we're exposed to. So we have the natural hazards like earthquakes, floods, and winds and volcanoes. I don't actually know volcanoes, but Jessie does. She gave me a presentation in class and taught me about volcanoes. She doesn't want to be called out. All right, we also have things like biological events, which I don't touch, but biological events can be considered natural hazard events. Growth of algae, for example, affecting a water supply. And then, of course, we have the man-made hazards, which, once again, I don't touch, but the anthropogenic industrial accidents. The rate of industrial accidents in the Houston area is just phenomenal. We think about Hurricane Harvey and the way it affected Houston, but actually industrial accidents down in that area occur at a pretty significant rate. And then chemical, technological, so the Y2K, fear, social, cultural, and economic disasters happen as well. I hang out in the natural hazards arena. And there's different ways that we can assess natural hazards. There are deterministic assessments. This is where we sort of say, okay, I want to think about what's the worst thing that can happen, and we design for that or retrofit for that. We can do scenario-based assessments. We look at some sort of set of representative scenarios of a hazard event that we might want to design or retrofit for. Or we hang out where I like to hang out, which is in probabilistic assessments, where we look at the likelihood and the likelihood of experiencing hazard events of various severities. What we're trying to do there is look at all, and I put all in quotes because there's no such thing as looking at all possible scenarios, and the relative likelihoods of occurrence, and we consider those in our assessment, and we represent it using this hazard. Typically we represent it as a hazard curve or a suite of hazard curves. We have one axis representing some measure of hazard severity, some measure of earthquake ground shaking, some measure of surge elevation, some measure of river discharge, for example, and then on the y-axis we look at the annual frequency of exceeding that parameter. So it's actually a frequency, but some people describe it as the probability that we'll experience hazards of various severities in a given year. This is where the notion of, if you've heard of the phrase, which I don't like, 100-year flood, it means 1 in 100 probability that elevation or discharge will be exceeded in a given year. Sometimes people flip those axes, but that's how I like to see it. All right, so the next step in disaster risk assessment is to understand your exposure. So what in your problem set is being exposed to a natural hazard? So this is thinking about what people might be exposed, what buildings, infrastructure, resources, cultural assets might be exposed to a natural hazard. There's many more. This changes with time. As I mentioned, one of the reasons disaster losses are increasing is because we keep putting building structures, people in harm's way. We like to build near water, for example. Lakefront, oceanfront, lakefront, riverfront property is pretty expensive. It's also where things tend to flood, right? So as we build closer and closer to these locations, we change our exposure over time. And then we think about vulnerability. And one way to think about vulnerability is our sensitivity to harm. And this could be physical harm, structural damage. That's the easy one. That's more where I'm more likely to do my work, but I will admit that's the easier thing to look at. But things like what kind of social harm can disasters do? Political harm. One of the big cultural impacts of disaster events is it breaks apart communities. As soon as the students can no longer use a school, it's a structure, it's a building. The building gets damaged. we can quantify the damage to a structure and what we think can happen to it. But that the damage to that school is not just the structure itself, it's that the students can no longer go to that school. And so the community members have to sort of scatter to go to other schools. They lose their support structure. Same thing happens with faith-based organizations, or if a medical facility is no longer available and a community doesn't have access to a medical facility. So these structures that I might be tending to worry about, yes, they do become damaged, but they actually have really big social and cultural impacts on communities that's probably more disruptive than the actual damage itself. And then we can talk about the impacts of health. And of course, these are affected by the presence of and the mitigation measures that we take that can reduce either our exposure by getting people out of places that are heavily exposed to hazards, or by vulnerability, by making structures more robust or resilient to natural hazard events. So I tend to work in this structural area if I do work when I look at vulnerability. So I think about vulnerability as we refer to as fragility. Has anybody heard the term fragility before? So fragility is our probability of experiencing some adverse state. The easiest thing to think about is the probability of a structure failing or otherwise becoming damaged as a function of some measure of hazard severity. So it might be the probability of a particular damage, exceeding some particular damage state as a function of ground shaking, or as a function of the elevation of water to which a structure is exposed. And so what we can do by mitigation measures is we can change the shape of this curve. So one option is, for flood events, elevating houses, right? This is a strategy that people use. Putting houses up on stilts is a great plan until it's not, right? Because at some point, a flood can be this high. So what you end up doing is maybe you reduce the probability of experiencing some adverse damage state for low levels of severity, but all of a sudden, you're going to jump up and you're going to hurt yourself. So depending on what we really want to do when we talk about fragility and mitigation is often we want to soften this fragility function. So we want to let the structure have a lower probability of failure or damage at higher measures of severity, but we don't want to just do it by creating this cliff edge effect. We want to soften the structure. And this is a part of the notion of resilience. We don't want to have these sort of cliff edges where all of a sudden consequences jump up pretty high all of a sudden. So that's this notion of sort of softening things. And just a note on when we talk about these mitigation measures, what do I mean? So mitigation can take the form of structural mitigation. So we can put dams and levees up on rivers. We like to do this to sort of keep the river contained, except once again, that's great until it's not. And the other bad thing is that as soon as you put these levees up, what do people do? Put their houses behind them. If you didn't put the levee there, they probably wouldn't build there. But as soon as you put that levee up, people go and decide to live on the other side of the levee. And so we actually we put a mitigation measure in place to change what we hope was changing our vulnerability. But all of a sudden, we've gone back and increased our exposure. Because we now have people that think, there's a levee there, I'm safe. And really, that levee is only so good as it can be overtopped or breached. And then we have other things that we can do. There's sort of innovative construction like base isolation. Or actually in the United States, one of the biggest hazards in, for example, earthquake events is falling components. Our structures are usually pretty good seismically, but things hanging from ceilings that are not properly anchored can be a pretty good hazard. I don't know if that one's anchored. It may not be. It might be great. But these sorts of things, roof tiles that can fall during an earthquake event, taking actions to secure building components. It can actually be a great retrofit strategy for reducing hazards during earthquake events. And then there's, particularly in the area of flooding, non-structural measures that can be really useful. So changing or making building codes stronger. You can actually see, for example, in the area of, when we're talking about high wind events, hurricanes, and other straight wind events, tornadoes are a different story, but we can actually see when we look at the damage assessments post-event, you can actually see basically where different buildings, you can actually look at a map, and by looking at the damage, you can sort of predict when they were built because of what building code they were built to. So we can have stronger building codes, or in some cases just adopt building codes, have something in place and some standard in place. We can use natural defenses. I mentioned some of the things like mangroves and wetlands actually do provide great natural defenses to hazards, at least for sort of lower level hazard events. They're not usually great for the big honking events that come through, but they do a good job for the sort of run-of-the-mill events that happen. Insurance is one good strategy. It at least reduces the losses. Of course, insurance is a challenge because only certain demographic groups are able to afford to insure themselves. So insurance is a bit of a tricky beast. You know, we try and change behaviors by offering incentives, educating and communicating with policymakers and members of the public about why it's helpful to take retrofit actions, why it's important to be prepared. This is, like I said, a big challenge. You know, we talk a lot about preparedness and making sure you have food on hand, but if you can't afford to have food in general, you're not going to keep 3 canned goods in your pantry when you're worried about feeding yourself today. And so these types of issues can be challenging that we work with. Risk communication is actually a really big challenge. And then there's warning systems. At least that gets people out of harm's way. And then we've talked about, okay, well, we want to know what hazards a particular location is exposed to. We want to know what the frequency is of experiencing hazard events of different severities. We want to look at, when we think about those hazard events, what's exposed to them. And then we want to think about what the vulnerability of structures and components that might be in a location are to a hazard. And then the next piece is looking at system modeling. And this is particularly important when we think about infrastructure systems. And this can be things like transportation systems, or it can be electrical distribution systems and water distribution systems, but it can also be healthcare infrastructure systems like pharmacies, hospitals, and urgent cares, and dialysis centers. They may not be physically connected like a transportation or electrical distribution system, but they work as a system. They provide services as a system. School systems, for example. So what we want to do is we want to look at the impact of these hazards on this overall system. So we may not need to have every pharmacy working after a hazard event, but we may want to make sure certain pharmacies are working and that they're distributed in such a way that everybody at least can get access to those pharmacies to get prescriptions refilled. Now, the pharmacy can be open and the pharmacy can be completely well stocked, but if it doesn't have power or water or the roads are blocked to get there, there's a dependency between these infrastructure systems. So, you know, we have the healthcare infrastructure, which depends upon the transportation infrastructure to create access, and they're also dependent upon the electrical distribution system and the water distribution system to keep those facilities open. The water distribution system has pumps that have to be run by power systems, so water distribution depends on the electrical distribution systems. So these are pretty complicated interdependent systems. So we have to think about these systems as a whole and the ability of these systems to serve the needs of the communities that depend upon them. So the key part of the risk assessment is understanding these systems. And then if we have these events and we have component damage and we have loss of infrastructure systems and the systems are no longer able to meet the needs of the community, we have to start thinking about the impacts or damage that can be caused by that or the consequences of that damage. So this, you know, the most straightforward is, okay, loss of life. This is a pretty straightforward one. We want to know if people are hurt by these events and what kind of damage, what structures are damaged, what infrastructure systems are damaged. But we also think about what are the economic and health impacts of those events. You know, what institutional services are lost, what cultural, historical structures are lost. You know, at any time one of these has, you know, Ellicott City has some great historical structures, right? But floods go through them and can do a significant amount of damage to them. So when we have these hazard events, you know, we have historical and cultural assets that can be damaged, and we can put a new building back, but it doesn't have the same cultural and historical significance. So we think about those. And like I had mentioned already, some of the impacts of damage to communities in terms of social cohesion and quality of life. I don't work in those areas. Those are hard questions, but they are important considerations. All right. And so in general, the whole theme of this is, if you haven't been exposed to what disaster risk analysts think about, these are the problems that we're thinking about. The bottom line is we do know that it requires a multidisciplinary approach. No one researcher, one topical area can solve any of these problems in the area of disaster resilience. So it requires both a multi-hazard and multidisciplinary approach. Even so much as, I always like this example, putting a structure up on stilts is great for flooding, but I don't know if anyone's ever heard of the phrase, you know, soft stories. We don't like big, heavy masses for earthquakes, So, that's great for a flood event, but it's really pretty terrible in an earthquake event. In the earthquake in Haiti that happened, well, a long time ago, it's over a decade ago now. One of the things is they designed a lot of their structures with big, heavy roofs because they saw hurricanes a lot. And big, heavy roofs are great for resisting the loads of a hurricane and the winds. But when an earthquake did happen, now they had big, heavy roofs, which are really are not what you want in an earthquake event, and it leads to collapse. So thinking about that. Now, they were designing for what they saw most frequently, which were wind events. And I'm not going to say that was a bad decision, but it's just understanding how designing for one hazard can really have adverse consequences for the performance of other hazards. So we need to work together is my message here, and we're talking about disaster resilience. All right, and so I promised I'd also mention some things about risk-informed decision-making. So we have all this great risk information. We can understand the frequency of our hazards. We can understand what the probability of damage is given levels of those hazards. We can integrate over that and get measures of probabilities of adverse states. We can think about our consequences. But then we have to do something with that information, right? Numerical information like that is only useful within the context of risk-informed decision-making. So I like to think about risk-informed decision-making in sort of using this graphic here. So we have a lot of what we just talked about a moment ago. We think about probabilistic hazard assessment, and we think about all the different types of hazards that we need to assess probabilistically. And then we think about how those hazards can affect individual components or people, and then how that affects the system. And then we take those numbers and we put that in the context of consequences. So the impacts on a region, both directly and indirectly. So often direct consequences are things like damage and economic loss, and indirect damages are things like the effect on people. And then we can come up with quantitative and qualitative measures of risk, things like expected losses or annualized expected losses. If we think about the probability of damage and we multiply it by the consequences, we can get an expected loss measure. But then we use this risk-informed decision-making. So I can, as a quantitative risk analyst, I can tell you the probability, or I can estimate, I don't know, I never know the answer for real. I can give you estimates of the probabilities of experiencing various hazard events. I can talk about the expected or the full distribution of possible losses. And I can tell you from an expected value perspective, quantitatively, what might be the best decision. But that decision can only be made within the context of a broader decision context. So decision makers aren't just thinking about what's the optimal from an aggregated perspective. We think about other factors like socioeconomic and political contexts. Or if I use a particular mitigation strategy, so for example, if I want to retrofit schools, and I do an analysis and look at the vulnerability of various school buildings, and I say, okay, well, given where I know, which school buildings are most exposed to the hazards, which are most vulnerable to damage, I run all the numbers on those probabilities, and I say, well, you would have the best, you would reduce your losses the most if you go and retrofit these 5 school buildings. But what if all those 5 school buildings are in very affluent areas? Is that equitable? It's very hard for me to put that equity into my quantitative analysis. So the decision maker has to think about those sorts of decisions in a broader context. Are we, by retrofitting these 5 schools, are we ensuring that the affluent communities have access to school after a disaster, but maybe less affluent communities don't? And in fact, those affluent communities may be the communities that have the ability to drive to another school in the event that there's a disaster event. There's less affluent communities that may not have that type of mobility. So those types of questions are pretty hard to deal with. But in the end, what we usually try and do is we try and look at as a risk analyst, folks may come up with these sort of ranking of alternatives based on various criteria. They get put into a decision context, and then somebody makes a risk-informed decision. So we've talked about the sort of social aspects of this, but risk-informed decision-making can also apply in more conventional engineering contexts. So if I'm designing, for example, a nuclear facility, or I'm looking at a nuclear facility, I may say that the risk of something is low, and so the risk numbers might suggest that you don't need to design against a particular hazard event because the risk is so low. But for example, in risk-informed decision making, I may say, you know what? Design for it anyway. I want to have some conservatism. So even if the risk numbers that you estimate tell me that the risk of something happening is quite low, I may suggest that you design for it anyway. I have this sort of like deterministic add-on that I think about when I think about risk-informed decision making. So risk-informed just means it's not risk-based. It means I don't just rely on my risk numbers, but I put other contextual or value judgments into my process. And those value judgments can be things like do it anyway, design for it, puts conservatism in, or it could be think about some of these other social economic contexts. So I'm going to change gears for a moment. I guess, do you have any questions on anything I've talked about so far? Pardon? Yeah. Okay. All right, so I thought, okay, so that was sort of the introduction to what some of the issues that we're thinking about in the Center for Disaster Resilience, as well as the Center for Risk and Reliability. We all work on little pieces of this larger puzzle, and I, maybe work on easier or harder pieces depending on our individual research interests. So I thought it might be useful to tell you a little bit about some of my ongoing projects that I have going on in these areas. I'm just going to sort of touch on them. They're all ongoing research projects. I've only been here at the university for not even a year and a half, so everything's ongoing. Everything's been started about a year and a half ago. So I'll share with you some of those research topics just to show you how I happen to be tackling some of these issues. All right, so actually one of the cool projects I have going on, this is my first venture into human subject research. I've never worked with people before, so I had my Institutional Review Board human subject training recently. So we're looking at flood risk communication. So one of the, I've talked about this notion of resilience, but one of the challenges is that it's very hard for subject matter experts to communicate risk information in general, but particularly in flooding events, with policymakers and with members of the public. One, it's that a lot of the work that we're doing is probabilistic in nature, and in general, we're all really bad at understanding and processing probabilistic information, even me as an expert in this area, and it's just not intuitive. It's not intuitive for anybody. So there's a big challenge with flood risk communication, but there's also natural biases and inclinations that we as humans have that makes it hard to communicate risk information. So basically people don't like to hear bad things. If you're worried about getting to your job every day and feeding your family, maybe you don't want to hear about the risks that you're facing, particularly if they feel a bit existential to you. So anyway, working on this project right now where we are trying to identify the challenges and opportunities for flood risk communication and why there's a disconnect between the knowledge that a flood expert knows, why people know that Hurricane Harvey was waiting to happen and nobody did anything about it. The subject matter experts couldn't convince people to do anything about it. And Hurricane Harvey is just one example of that. So what we're doing is we're actually interviewing subject matter experts in a range of areas, people with expertise in hazard and risk management, but also in emergency response, people who actually are on the ground dealing with these problems. And we're using some qualitative research methods to identify key insights and themes on why this is such a challenge. Every time I go to a conference, this always comes up as a problem. We don't know how to communicate risk. So we're doing some work here. And I'm working with Dr. Harovic, who's a risk communication expert and also knows how to do human subject research. So she's awesome at working with me on this. So outside of that area, I have a couple of research projects dealing with nuclear facilities. So nuclear facilities are a unique beast. Our risk tolerance when it comes to nuclear facilities is pretty darn low. So we deal with much more severe events. We design for much more severe events at nuclear facilities than you might do for standard infrastructure systems. So for that reason, we deal with issues when we're dealing with design and analysis of nuclear facilities that may not pop up when we're dealing with other types of infrastructure. So one of the topics that I have that actually and my students is working on right now is looking at spatial variability of seismic ground motion at nuclear facilities. So in nuclear facilities, you often have several different reactor units, several plants located rather close to one another. And we want to do an assessment of the risk of that facility. And we need to think about both of those units. But when we're thinking about the ground motion, we often at this point assume that the ground motion under those two units is exactly the same, but it's not. Even at the scale, and you probably know this much better than I do, but even at the scale of 100 meters apart, those are pretty close together. But the ground motion that the two structures located 100 meters apart might experience can be different in a meaningful way. And if we want to assess the seismic risk of a nuclear facility in a realistic manner, we need to understand how this ground motion can change. Actually, in many ways, probably assuming perfect correlation may be conservative, but when we're doing risk assessments, we don't want to be conservative. We want to be realistic. We want to assess the actual risk. So the project looking at that and using some Bayesian networks to look at this because I love Bayesian networks and they show up a lot in my research. So, all right. Also staying on that nuclear power plant theme, I mentioned that we worry about issues with nuclear facilities that may not rise to the surface with other types of infrastructure. So one of those things is looking at combinations of flood hazard mechanisms. So in certain environments, you can actually be subject to multiple flood mechanisms at the same time. So if you think about a location that might be located on a river that's just sort of upstream of the mouth, we talk about tidally influenced rivers or estuary environments. When a hurricane comes through, that hurricane can generate surge that will actually propagate up the river to some ways to affect the site. At the same time, that hurricane's dropping rain, and that rain can run off and cause a rise in the river level, or increase in the river discharge and a rise in the river stage, and these things can come together in a quasi-superposition. And that same rainfall event can be causing rain on the site and causing ponding on the site in low-lying areas. So there's actually no strategy right now for dealing with these types of events and characterizing them probabilistically. So I have a project going on right now where we're looking at how, what the current state of practice is, what we can do. So the one I just described is a way of looking at when we have two different flood hazard mechanisms, like river flooding and storm surge being affected by a common hurricane, leading to a flood hazard, which is potentially more severe than either of those hazards would have been by themselves. We also can think about things where one hazard creates another hazard. So for example, an earthquake can cause ground shaking at a site, but can also cause a tsunami or a seismically induced dam failure that then leads to subsequent flooding of the site. And things can just also happen independently. Those are much less likely, but you can have a hurricane when you just happen to be having a river flood at the same time because there was a rainfall event a week earlier. So you have things can happen independently. So we have a project looking at that. Right now, I'm working with Dr. Weaver. We're looking at what we refer to as epistemic uncertainty in hazard assessments. So epistemic uncertainty, there's two broad classes of uncertainty, aleatory variability and epistemic uncertainty. Aleatory variability, this is natural randomness. This is things like we just don't know when a hurricane's going to hit, and we don't know what the characteristics of that hurricane's going to be. Epistemic uncertainty arises from the fact that we can interpret our data models and methods in different technically defensible ways. So 2, 3, 4, 6, 10 perfectly competent analysts can look at the same data and come up with completely different conclusions. They can decide that different methods are appropriate. And this leads to uncertainties that we want to consider in our probabilistic hazard assessments. So in this example here, this is looking at hurricanes impacting a region along the North Atlantic coast, and I just made very slightly different assumptions and used a slightly different mathematical technique, and I get a pretty different estimate of the rate with which hurricanes will impact that area, going from 0.17 to 0.23 in terms of the rate at which we think hurricanes can happen. And I can make a lot of these different assumptions, and then I look at these in the context of those hazard curves. So I showed a hazard curve earlier, and I said we characterize hazards using this hazard curve with severity on one axis and the probability of exceedance on the other. Well, making all these different assumptions can lead me to a whole bunch of different hazard curves. And looking at this uncertainty and how we can deal with this uncertainty in our probabilistic assessments and subsequent risk analyses. So I have a project right now that's looking just at these epistemic uncertainties in storm surge hazard assessment and understanding what the heck this range is, how big can this range be, and what do we do with it. So this has implications that the 100-year flood could be a pretty big range in terms of how big it could be. And then this project here, so looking at storm surge surrogate modeling. So when we're looking at storm surge hazard assessment, we need to understand how hurricanes of different parameters can generate surge at a location. And in order to do that, the best state of practice right now is currently using high fidelity numerical models with lots and lots and lots of elements and nodes, and they are really expensive to run. I mean, take $100,000 computers and run them for a week, and we'll get a run. These are very expensive to run. So for my calculations, or for the calculations that other people who do probabilistic storm surge hazard assessment, we need to run a lot of these calculations in order to develop that hazard curve. Well, that's really expensive. So what we're trying to do, I'm looking at this, but there's other researchers that have looked at this as well, and I'm working with some folks at Virginia Tech, is can we develop physical process model emulators or surrogate models where we use things like machine learning techniques to develop surrogate models that behave close enough to that complicated numerical model, at least for the purposes of our analyses. So folks have had, some researchers at Notre Dame have had a lot of luck in doing this with large-scale data sets and dense data sources. We're looking now if we can couple that notion of machine learning with physical process knowledge, so knowledge that a subject matter expert has of a physical process, and using that knowledge to scale data and couple that with a machine learning algorithm to develop better predictions with less numerical model runs. And the other issue here is that not only do we want to be able to do this, but we want to understand the error structure. So errors are not a bad thing. Errors are only a bad thing if you don't know what the error structure is. So I can handle error. I just can't handle error that has a lot of stochasticity to it. So we're looking at, can we do this in a way where we have a well-defined error structure? We're also looking at ways to potentially, we don't know if this will work, but can we map knowledge about out here, something about if we know the surge out here where the model is very cheap to run, can we develop a probabilistic mapping to the coastal location where it's expensive to run? We can run lots of models that are cheap and use some sort of well-defined error characterization and probabilistic mapping to map that, that surge in a probabilistic way. So wrapping up, so I have some other projects that we're looking at now. We have a project with Dr. Riley and Zainab, a student in civil engineering, looking at the impacts of climate change on agriculture in Maryland. So how potentially building predictive models so that we can understand if rainfall becomes more severe or less severe, how that might affect agricultural productivity in the state. I have a project working with somebody at one of the national labs, actually mapping some of these techniques that we use in natural hazards to looking at adverse navigational conflicts, not ship crashes, but incidents where things get a little too close for comfort, and looking if we can use some of the natural hazard techniques we've used to look at these types of problems. Looking more at uncertainties in probabilistic storm surge hazard assessment, and there's also a project that's just getting underway looking at the impact of sea level rise on brownfield sites. So we have a lot of brownfield sites. Brownfield sites are places that are polluted or for some reason, chemical facilities, industrial facilities. You don't want to live there. But what happens, how many of these things are potentially subject to sea level rise? Could be inundated. We don't like to put water on top of polluted sites. Water tends to carry that away. And a quick plug, we have just recently rolled out a series of courses in resilience engineering in our department. So we've got courses looking at natural assessment of hazards. That's my course. Dr. Riley's teaching a course in infrastructure and resilience. She does optimization and looking at all the different complicated ways that we can think about risk. There's a class in fire protection. We offer a disaster resilience seminar on Friday. Right now it's Fridays at 11 a.m. So if you don't get enough seminar action on Fridays, you're more than welcome to come over and hang out with us. And then next semester, Dr. Sandra Knight's teaching a really cool course in disaster management and some of the challenges of the post-disaster environment and managing disasters. She has an incredible amount of experience. And then there's a course in project management, and our disaster resilience seminar is going to continue. That's all I got.
So what happens when you have a disaster that's a very low in, like it happens once every, say, 10,000 years? can you start to factor these same kind of models in for those, because maybe the unknowns are larger?
So it's a great question. So we don't talk, so it's something that has we deal with events that have a probability of 10 to the minus 4, 10 to the minus 5, 10 to the minus 6 per year frequently. So we actually do characterize those hazards, or at least particularly in the area of nuclear facilities. Most standard infrastructure is going to be designed for 100, 1 in 100, 1 in 1,000 types of events. But nuclear facilities, you're dealing with events that go out into those types of probabilities. Those epistemic uncertainties I talked about, that's when they really start to matter. You don't know, and so and you don't have any data to really tell you what things look like at those extremes. And so that's why dealing with these epistemic uncertainties and understanding, do we have to think about all those different interpretations? I can tell you we don't have to think about all of them. Some of them may not be fully technically defensible, but the point is that they're there. And those types of events, those really infrequent ones, that's where the epistemic uncertainties can really drive our answers and what those types of events are and what their characteristics are. So, yeah.
I'm wondering about how often you'd say that cities or people learn from past disasters.
So this is not my area of expertise, so I'm going with anecdotes from people who know this.
Okay.
But it's about, my understanding is about a year. That people start forgetting about events after about a year. So there is a complicated, and Dr. Riley, who works in my department, does look at this issue of whether or not your future resilience is affected by your past events. Well, if past events could have set you back in terms of your ability to become more resilient, right? Something could be damaged and have never been repaired, and then that sets you back. It could also mean that because you've experienced an event, you're more likely to take actions. So my understanding is in Houston, for example, people are actually buying flood insurance more right now after Harvey, and they're also doing things to improve the drainage in their yard. So they're taking these actions. But I think my understanding is that as time goes on, a year, 2 years, people stop. Their institutional memory goes away, and they stop paying their insurance premiums because if they're not required to have that insurance, and they may not worry about paying to maintain the drainage in their yard. So does that answer your question?
Yeah.
But I am not an expert in this, so I'm working on anecdotes from people who do know.
Colin, did you have a question?
Oh, I was going to ask you about the what model you were using for the storm surge. But the NOAA SWASH model or something?
That one is going to be, I don't run them. I have collaborators that do. They're using AdCirc and AdCirc plus one, typically. There is one project we're looking at some lower fidelity. So mostly it's high fidelity AdCirc models, some low fidelity AdCirc models, rarely slosh.
Right, so
because slosh is cheap, so I don't need to do this.
It's cheap, so yeah. So I was wondering if you also compare the less expensive models that incorporates, like SWASH, that doesn't incorporate some of the morphology of the coastline, but is cheaper to run than the high fidelity models, or are you using the high fidelity models as a standard that you're comparing everything to?
Right now we're thinking about using the high fidelity models as the standard, but there's not a lot of work right now in this area of the characterization of the error structure. And understanding whether or not the high fidelity surrogate model buys you something more over what slosh might do with a well-characterized error structure is a very, very fair question. And right now, like I said, the folks at Notre Dame have had good luck with using Gaussian process regression in emulating AdCirc, but they haven't really described their error structure and explored their error structure very well. So those types of questions is something that's really interesting to me.
It's been tested very well against actual storm surges. The Hurricane Sandy gave us a great ability to test, a couple of these models, and surprisingly, some of the ones that were lower fidelity seem to be working just about as well, and almost all of them got the effects of both hardened structures and soft shoreline well. So they didn't have the right algorithms for what the marshes are actually doing, etc.
Yes, that's a great point. So when we're trying to build a surrogate model, either the techniques that have been used by others or the type of processes we're trying to use now, the strategies we're looking at now, we're comparing back to a numerical model. But really what we care about is how our prediction compares to reality. All we can do is compare our prediction to the numerical model for all the runs that we have available, our surrogate model to the numerical model, but we have only a few hurricanes with which to validate our actual numerical model to reality. So it is a bit of a complicated challenge, and it's something that I think we really have to think about.
It kind of reminds me of back when Aleatory and a couple other people said, oh, let's just check our most complicated rainfall runoff models, one that's more physically based, with ones that are less physically based but simpler and easier to run. And they sat down and sort of did the analysis with reality, and it was like, you know, the best physically based model did not do the best because you don't actually have all of the details to put into the model, and so you're short of the information to make that model work correctly. And so I'm thinking if you're basing your answer on this best model, which is always limited in its data, filling out the database for that model.
Yeah, I would actually go
Questioning that, yeah.
I would go one step further, because I have these people who they sort of say, oh, all these complicated physics, and I need to run this expensive model. But in the end, I showed this picture. I was like, I could tweak the way I filtered the data in hurricanes, and I can shift it by a meter in terms of what the 1,000 annual exceedance probability event is anyway. So do I care? I'm not sure. I'm not definitively sure on this, but I have some spidey sense that maybe it doesn't matter if my numerical model is that great, because of the epistemic uncertainty may be overcoming that and being much more dominant than what the numerical model is. We actually have a project right now looking at, can we go ahead and quantify that relationship? This is completely spidey sense. Yeah.
So I want to ask about engineering. So you talked about fragility, and I've been reading about anti-fragility in the sense of like Talib's idea. Do you know this literature?
I don't know the literature well, but I've heard a few sort of concepts.
It's this idea that some phenomena, some structure actually thrives on stress. Instead of being crushed by it, it actually does better. Is there any example of that? So the only example I can think of with that is life in general. But is there any example of that in the builds or the societal world in which we have anti-fragility?
I'm sure there are. That is way outside my wheelhouse. I mean, structure systems. I mean, there are certain structural materials that will become stronger under compression.
Yeah, or when there's weather, right?
Yeah. So there's certain things that you think about loading something that the material can become stronger under compression, but very weak under tension.
Is that part of building?
Oh yeah, we think about those types of things. In terms of just the simple structural loads, what becomes stronger and what becomes weaker under compression. But typically, when we're doing a risk assessment, we don't get that complicated. We don't take the optimistic view. The same thing can happen with. There's an argument that sometimes when soil liquefies, that it can actually reduce structural loads. We don't credit that ever. You don't ever want to count on a bad thing happening, because you can technically put it into we typically will only put it in, like in a nuclear facility risk assessment, we will only put beneficial failures into the system if neglecting them would distort our risk insights. And that's probably just a philosophical approach.
I love that term, beneficial failures.
We actually use that right now in the standard. But yeah, so
something collapses and prevents something else from working.
Great idea.
yes, yeah. So we don't tend to credit the collapse that can prevent something, unless it's sufficiently likely that if we didn't include it, we would distort our risk insights.
Expect the worst and hope for the best.
Yeah.
Okay.
So.
More questions? Yes.
I was just wondering, the communication stuff, you said it's ongoing research, but with all the breakthroughs in like the statistics and the computing and the forecasting, what are like bureaucrats' excuse for being so underprepared? Like, why do people just not listen? Like that's.
Exactly.
I was wondering if you had some further something to say about that.
So we have not. We're actively engaged in those interviews right now. So we have not done the qualitative assessment of it. But just sort of from a preliminary perspective, one, we all are really bad at intuitive reasoning with probabilities. So if I throw probabilities at you, one, if you've never taken a class in probability, you're not even going to know what that means. Maybe I can make it into the context of gambling. Maybe that might work. But it's sort of hard to communicate probabilistic information. There's been more success with things like showing red, green, yellow, sort of basic communication strategies. Sam Brody at Texas has a really cool tool called Buyer Beware, and it looks at what properties have been flooded, the idea being that people can go and look at that property before they buy it, and it'll be red, yellow, or green. And sort of red's bad, yellow's green is okay, you're good to go. Now somebody had to make the judgment on those colors, but that seems to have had some success because it's been simplified. But the thing with policymakers is they're not just making the best decision. They're elected every, 4 years? If they have to do a strategy that's going to take 10 years, or it's only going to cost money for the next 4 years, and you're not going to see the benefit until if a hazard event happens or 10 years down the line, what's their incentive to do it? They're worried about getting elected next session. And so putting a bunch of money into something now, which takes away from your ability to put up a new playground, may not be politically popular. So those like I said, not my area of expertise, but those types of things. So it's not that they just have different value systems and maybe different priorities in a particular moment. And it's not just that they want to get reelected, but they have to choose. Do you put more textbooks into school, or do you build a flood wall? The flood wall might not be needed. The event may never happen, but the textbooks might be. So these are, it's a complicated question. Yes.
Have we seen any changes over the past decade or longer in how much people trust or listen to risk assessments? We talk a lot about, just in the last year or two, distrust of scientists. Does that bleed over into this as well? Is it getting better? Is it getting worse through time?
I don't necessarily know if it's getting better or worse. These are the interesting questions that I don't study. I do the math part, which is a little easier. My understanding, some of the cultural things about distrust of government or distrust of authorities. So, for example, in disaster events, sometimes emergency managers are former law enforcement personnel. If a community has a natural distrust of law enforcement, and then a person gets up in front of the media, and they have a badge on their shirt, and they have a sort of a demeanor that's similar to law enforcement, that may inherently create distrust. So some of those, from people I'm reporting anecdotes here, but that types of things can be having a play. But I think that like in Houston, my understanding is that the uptake of insurance has increased, but there's sort of these short timelines. So I don't know what the answer is, but I do know that there's a whole bunch of complicating factors in terms of the trust of the government and the impact, and I know that some studies have had a lot of success, like working with faith-based, or that the leader of a faith-based organization may have a better ability to communicate about what people should do for preparedness or resilience than somebody coming in from the outside. And these sort of native approaches have shown some success.
So I guess education is very important. Lucky we're all in the school. So let's thank Shelby again.
Bring the rest of the conversation back to geology.